All right. Welcome, everyone. So today we're going to start talking about chapter 17, okay, on different aspects of aqueous equilibrium. We'll talk about titrations and KSPs and things like that in this chapter. So we'll get to those type of things after the exam. That's next week. Okay? Today we'll mainly focus on buffer solutions. Okay? So again, as a reminder, right, next week, Monday, there's an exam, right? For those who are in class today, right, on Wednesday, you will take the exam on Wednesday next week, right? I sent out an announcement recently and updated the Canvas website some for just some study guides, tips, and other things like that for exam 2. Okay, I uploaded a document that has a rough list of kind of topics or concepts or types of problems, right, from each chapter that you're familiar with and know how to solve, and as well as then lists of equations that either you need to know or need to know how to use, and then lists of resources, right, that you can go to in class, right, to study for the exam, as well as for practice exams 2 and 3, which questions to review in those practice exams, okay? So, right, so previous semesters I've taught this class, I've done 4 exams through the semester. This semester I'm doing 3. And so exams 2 and 3, right, have questions related to this exam. So don't just look at practice exam 2, but look at practice exam 2 and 3. But pay attention to specifically the problems that I marked in the kind of study guide, if you will, for which questions to go over, both multiple choice and the long answer questions, okay? All right, and again, I mentioned some of this stuff in an announcement that was sent out, as well as just on Canvas, I created a new module for, like, I think I called it like exam 2 info or something like that, that has those files linked to it, as well as practice exams linked in that module, as well as solutions to odd number homework or textbook questions, right? I also posted online answers to participation questions we've done in class. It's just other things you can kind of go over and review, right? So yeah. Any questions before we get started on chapter 17 today about the course, about exam 2, or otherwise? Also, I'll remind you, right, that you have a quiz on chapter 16 that is due today. I can't remember the due time, so check on Canvas, right? But it's due by this evening. It's already been available since yesterday afternoon. And again, it's due today, this evening, as well as your sapling homework on chapter 16. Okay. Oh yeah. Any questions? Yep.
Just to clarify, you said for exam 2, we should look over practice exams 2 and 3.
Yes, 2 and 3, but not all of the questions, right? So there's on Canvas. I mean, you can find it in the module. You can find it in the announcement that I sent out. And things like that. But there's a file that's like fall 2020 exam 2 review notes or something like that. It has a list of questions in exam 2 and 3 to look over. Try to hold on to Canvas real quick. that, but just to kind of make sure and verify that that is there. I'm not lying to you. All right. All right, so I linked the module as well and kind of the calendar, right? Exam to info module. That has, so the study guide that was uploaded, as well as answers to participation questions that are given class. Again, practice exams that are relevant to this exam. In-class examples and their answers that we've been going over, right? As review in the textbook solutions are all kind of linked there, right? And then for that file, again, you have a list of kind of concepts for the different chapters, talking about different equations to be familiar with and or memorize. And then for the practice exams, 2 and 3, which multiple choice questions and long answer questions to consider when reviewing those exams. Okay. Kind of are all there. Okay. Other questions?
So last time for exam 1, you did like a Zoom meeting thing where you like explained stuff you know and go over examples. Are you going to do that again for this?
Not really. I had like 2 people or something, like 1 person show up in person and like 2 or 3 people show up on Zoom. So, so that's why I made this study guide. It has the information, again, equations that you need to know and things like that on that file, and such. But yeah, I'm happy to have, set up Zoom meetings with anyone who has questions and things like that at any time. Email me questions, happy to answer them, things like that. So again, feel free to come to me with questions that you have and such, but I don't have any kind of review session planned to do for this exam. So, but again, all the information on that was at the beginning of that study session in terms of what concepts and what to review and what to go over is in that exam to review document. So. Other questions? Screen here. All right. And for those who are taking the exam online, I'll send out some announcements to you just to remind you about when you're taking the exam, right? How to take the exam and things like that. It'll be the same as exam 1, but I'll just send out friendly reminders about it. So, all right. So let's get going then, if there are no questions, right? So again, chapter 17 is going to be just kind of continuation of talking about equilibrium. And in the first part of the chapter, we're talking about more types of acid-base equilibrium and acid-base chemistry. And then the second part of the chapter, we're going to talk about the solubility of solids and solutions, salts, right? So far, we mainly just talked about salts that are strong electrolytes that fully dissociate, sodium chloride, potassium chloride, things like that. But we'll talk about solids that don't completely dissolve in solution and discuss equilibrium established there and things of that nature. Okay. Again, in terms of exam 3, just this stuff on buffer solutions that we'll kind of get to today will be the only things relevant from chapter 17 on this exam 2. Sorry, I think I said exam 3, but on exam 2, right, it's the only thing that's relevant, the stuff on the buffer solutions that we'll get to today. Okay. So related to this buffer solutions, right, let's talk about review of our LeChatelier example, right? Let's say I have a solution of acetic acid, right? Where acetic acid is a weak acid, and it establishes this weak acid dissociation equilibrium reaction, right? HA, acetic acid, associates into hydrogen ions plus acetate ions, right? It's this weak equilibrium, has an equilibrium constant that we call K sub A for this acid dissociation reaction, right? And the question is what happens to this equilibrium when sodium acetate is added to the solution? Okay? Any thoughts on what might happen to our reaction here when we add sodium acetate? Yeah, right. So the idea, it will reform acetic acid because what you're doing, right, is sodium acetate, right, is, using kind of the notation here of A minus is sort of the acetate in this equilibrium reaction, right? If I were to write out the actual formulas, right, you'd write this as HCH3COOH, or sorry, not H up in front, right? CH3COH going to H plus CH3COO minus, right? And and then sodium acetate, right? It's NaCH3COO, which just dissolves completely in solution to form sodium ions plus acetate ions, right? And so these acetate ions, right, get added into solution, right, which according to the Neutralization principle, right, we've added a product, right? And so because of the addition of this product, our equilibrium is going to shift to the left, right? And I'm going to reform some of this acetic acid, right? Right, so I've added sodium acetate. The acetate ions are a common ion in this equilibrium reaction that's established in my solution. And so that common ion, right, that acetate is going to cause this equilibrium to shift to the left. And I'm going to reform some of my acetic acid that had broken apart originally in the solution before the addition of sodium acetate. Yeah.
Nothing happens to the sodium ion.
Nothing happens with sodium ion. Yeah, sodium is what's considered a spectator ion in the solution, right? It's sodium, as we kind of talked about, I think it was last time, I forget, right? That sodium, potassium, lithium, chlorine, bromine, iodine, nitrate, a lot of these very common cations, anions, right? That are sort of the conjugate acid, conjugate bases, if you will, of strong acids and strong bases, right? Are spectator ions in solution. They do nothing in solution. They'll never be involved in any relevant chemical reaction. They'll just be floating around in solution doing nothing. Okay. So yeah. Right. And that example, right, with this acetic acid and sodium acetate are examples of strong electrolytes and weak electrolytes, right? That we've been talking about, right? Strong electrolytes, things like a strong acid, strong bases, salts that we've been talking about so far, right? All fully ionize, fully break apart into solution, right? Sodium acetate fully breaks apart into sodium ions and acetate ions when they put into solution, right? While our weak acids and weak bases, right, are going to be these weak electrolytes that only partially dissociate, okay? Right, and so when we mix these strong electrolytes with electrolytes, okay, specifically a strong electrolytes that have, say, the conjugate base to, say, a weak acid, right? Right, that strong electrolyte is going to dissolve, and then it's going to affect the equilibrium such that the equilibrium is going to want to try to reestablish itself by recreating some of the weak acid or weak base, right? So again, right, in this reaction, we introduce some acetate ions through the addition of a strong electrolyte. Those acetate ions then cause the reformation of acetic acid here, right? And so in those solutions, right, a solution, say 0.1 molar acetic acid versus 0.1 molar acetic acid with 0.1 molar sodium acetate, which solution has a smaller percent ionization of that acetic acid? Right, percent ionization, right, is sort of what is the percentage of your compound that broke apart in solution. Strong electrolytes, right, have 100% ionization, right? Weak electrolytes are less than 100%, right? And so if I'm looking at the percent ionization of acetic acid, right, I'm asking which solution has less acetic acid breaking up in solution. Yeah, it's going to be solution B here, right? As we've been talking about, right? Because of the addition of that acetate, I reformed some of my acetic acid, right? So some of the acetic acid that had broken up in my original solution is now reformed. And so I get less of the acetic acid total that has broken apart, right? I've reformed some of the acetic acid through the addition of the sodium acetate in order to reestablish that equilibrium according to the LeChatelier's principle, right? And so, right, that means that the percent ionization of acetic acid is less in a solution with 0.1 molar sodium acetate than it is in just a pure acetic acid solution. Okay. And again, all this basically just boils back down to LeChatelier's principle, right? That we added some of the products in this equilibrium, so it's going to shift to the left to form some of the reactants, which means less of my reactants have broken apart to form the product, so I get less or a smaller percent ionization. Question? All right. So again, just talking about general solutions and things like that. We make solutions with the addition of different compounds, right? So let's say I have a solution of HNO2 and KNO2 mixed together, right? Question is which ions in the resulting solution are spectator ions, and right, what is any of the acid-base chemistry that's occurring, right? And what potential equilibrium is established that determines the pH. So the first question here would be, right, when looking at this question, right, one of the first parts to ask yourself, out of these things, what of these are, which of any of these are strong electrolytes and which of any of these are weak electrolytes, right? So is HNO2 going to be a strong electrolyte or a weak electrolyte? It will be a weak electrolyte, right? Any acid that is not a strong acid is a weak acid, right? And a weak acid is a electrolyte. A strong acid is a strong electrolyte, right? Again, strong acids 100% dissociate. Weak acids only partially dissociate and establish an equilibrium, right? So any acid that, again, is not on that list of strong acids that you need to remember, right, is going to be a weak acid. And so this is a weak electrolyte, okay? And so KNO2, that is a weak or strong electrolyte. That's going to be a strong electrolyte, okay? Right? So, right, basically any salt we've talked about so far are strong electrolytes, right? So this salt here, the strong electrolyte, right? So HNO2 in solution is a weak electrolyte, so it establishes an equilibrium reaction, right, where it partially dissociates in solution, while KNO2 is a strong electrolyte and will form K plus NO2 minus in solution, right? So this goes to completion, right? It fully dissociates, so I just have K plus and just have NO2 minus in solution. All this establishes an equilibrium, okay? So what out of these things is a spectator ion for this problem? Right, the potassium, right? Right, a spectator ion is some ion, right, that's not involved at all in any of the chemistry, right? Potassium is a spectator ion, right? It's always going to be a spectator ion, just like sodium will be, lithium, chlorine, bromine. Again, like we talked about at the end of chapter 16, some of this stuff when we talked about the or the pHs of salts, right? Any of these ions that come from strong acids or strong bases, right, are going to be spectator ions in solution and not undergo any sort of acid-base chemistry that we talked about, right? So K plus, right, potassium is a spectator ion, right? Right, and they're called spectator ions because that's what they do. They just spectate the reactions, right? They do nothing, just hang out, view, see what's going on, right? And so then the relevant equilibrium and the relevant chemistry that's going on in this problem, right, is related to this weak acid dissociation equilibrium reaction, right? So that's kind of the question. The second part, right, what is the equilibrium involved, right, that determines the pH, and it is this equilibrium right here. All right. So questions about this example? All right. So then let's consider an actual solution of this and calculate its pH. Okay. Okay. So this is kind of the first example, or I guess second example, and the examples hand out here in class. Those examples are also posted online. So let's see here. The question on Zoom here is that one chosen because it has no spectator ions. So HNO2 and its equilibrium is chosen to be the equilibrium that determines the pH just because it's an acid, and so it itself is going to determine the pH, right? Technically, right, you could say, let's go, right? Technically, you could have also said, well, I got NO2 minus in solution, that's a weak base, right? NO2 minus reacting with water forms HNO2 plus OH minus, okay? And this is all, like, this could have also been a valid answer to what equilibrium is determining the pH, right? Because if you used either of these two equilibrium expressions, right, this is the equilibrium constant Ka, equilibrium constant Kb, right? And if you know what the values of those are, right? The fact that these are conjugate acid-base pairs, right? So Ka times Kb equals Kw, right? So these things are related to each other, and no matter which equilibrium you picked, you'd get the same answer for the pH of your solution in a given problem, okay? I just went with the weak acid equilibrium, but you could have picked this weak base equilibrium for the conjugate base, okay? But I know that I've added a weak acid with its conjugate base in solution, and so there is no other chemistry going on besides just an established equilibrium between that weak acid and its conjugate base, okay? There's no other acid-base chemistry going on, okay? Because a weak acid will never react with its conjugate base, okay? It's a very common thing that I see people do where they'll say, oh, I have HNO2 in solution and I have NO2 minus in solution, and this is going to react in some way to form something, and they'll, form some compound, I don't know, right? But they'll try to undergo some type of chemical reaction with a weak acid and its conjugate base, okay? And this does not happen, okay? A weak acid does not react with its conjugate base. Instead, a weak acid and its conjugate base establish an equilibrium between each other, okay? Right? So if you ever have a weak acid and conjugate base in a solution, those things are going to just establish an equilibrium between each other. They're never going to react with each other, okay? All right, so going back to that example, I guess I should have just stayed here, right? Okay. So I want the pH of this solution, right? So I'm looking for the pH of a weak acid, right? Where my weak acid is HNO2. Right? Ka is 4.5 times 10 to the minus 4. Okay. The equilibrium constant expression is equal to what? Like the expression itself, obviously not the numerical value, but the expression. So yeah, so it's related to Kw and Kb. I guess what I'm looking for is concentrations of products and reactants and things like that, right? Your equilibrium constant expression for this equilibrium reaction is going to be concentration of what divided by concentration of what? Say that again? Yeah, so I'll have NO2 minus, right, the base, and I'll have the acid, HNO2, and I will also have H plus, right? It's an equilibrium constant, right? So it's just the products divided by the reactants, right? Raised to their stoichiometric coefficients. Again, right, I know we have these subscripts A and B and W and things like that, but these are all just equilibrium constants. So the expression for the equilibrium constant is the same as all equilibria we talked about in chapter 15, right? Concentrations of products divided by concentration of reactants raised to their stoichiometric coefficients, right? Every time we got an equilibrium, right, we can always write out that equilibrium constant is the products divided by reactants, okay? So the concentration of NO2, 2 here, right, times NO2 minus times concentration of H plus divided by the concentration of HNO2, okay? So what am I going to have to use here to try to find that equilibrium concentration of H plus to get the pH? I have to use our ice table, right? Ice table, ice chart, right? Okay. So our initial concentration of NO2 told is 0.085 molar, right? And then we also have a concentration of nitrite, okay, NO2 minus of 0.1 molar. Because again, right, KNO2 breaks apart the K plus NO2 minus, right? So every mole of KNO2 forms 1 mole of NO2 minus. So 0.1 molar KNO2 forms 0.1 molar NO2 minus in solution, right? Concentration of that NO2 minus is equal to the concentration of potassium nitrite. And then my initial concentration of H plus is 0, right? So then I'm going to do our change here. Since I have no H plus, I got to add some amount of H plus, right? So I got to add to the products, okay? And I got to take away from the reactants here. Okay. Now, again, what I'm going to do for this weak acid equilibrium, right? I got a fairly small equilibrium constant, 4.5 times 10 to the minus 4, compared to my concentrations, okay? There are about a factor of 1,000 different, at least, between the concentrations, the equilibrium constant. Okay, I'm going to make the approximation, right? X is very small, which isn't an approximation, but I'm going to use the fact that X is going to be very small. So I know that 0.085 minus X is approximately 0.085, right? 0.1 plus X is approximately 0.1. And then 0 plus X is X. Okay. So again, right, these two things here are approximations that are very valid to make for any weak acid, weak base equilibrium. We'll be making this type of approximation, right? That the concentrations of the weak acids or weak bases, if they exist, right? If they're non-zero, are going to essentially not change when establishing the equilibrium, right? And so when we use that, we can plug all that stuff in, because these are now our equilibrium concentrations. So I can plug that into my equilibrium constant expression. And now that 4.5 times 10 to the minus 4 equals the concentration of NO2, which is 0.1, times concentration of H plus, which is our X, divided by concentration of HNO2, is 0.085. Okay. Right. And so going through all of that, right, you can solve X here. And you will get that X equals 3.8. Let's leave it 3.8 times 10 to minus 4. Okay. Molar, right? And again, that X is our equilibrium concentration of H plus, right? Because again, X here, right, is the equilibrium rho for for H plus, right? So the concentration of H plus at equilibrium is equal to 3.8 times 10 to the minus 4. So the pH, right, which is just the negative log of that concentration, right, is 3.42. Okay. Okay.
Another question.
Yep.
It might be unrelated, but what is pKa again?
So pKa is equal, pKa is just the negative log of Ka. And we'll talk about the Henderson-Hasselbalch equation, which uses the pKa in kind of the next example when we get to it. But yeah, so the P of anything is just the negative log of that thing. So pKa is equal to the negative log of Ka. pKb is the negative log of Kb. pKw would be the negative log of Kw, right? Just like the pH is the negative log of the H plus concentration. Okay. Other questions? Yeah, so basically, I look at my concentrations here, okay, and comparing that to the equilibrium constant, right? It's almost a factor of 1,000 different between the two, or at least a factor of 100. Let's see here, a factor of 100 different between the two. So, so based off of that, I'd say, I use that to say, okay, the change in X is going to be pretty small. And you can always check your answer, right? If I look, right, using this approximation, I got that X, my concentration of H plus, is 3.8 times 10 to the minus 4, right? So if I did 0.085 minus 3.8 times 10 to the minus 4, rounded it up to two significant digits, I'd get 0.085. So, right? And so, yeah, so it's a very reasonable approximation to make. But yeah, that's typically how I look at it. In general, any weak acid, weak base equilibrium problem like this that you deal with, you'll be able to use that approximation. I'm not going to put something on there where you can't, because then you have to use like the quadratic formula or something like that. And but if you're like in lab or something like that and not unsure, right? Ways you could check is, again, comparing your initial concentrations to the equilibrium constant, as well as just use the approximation and then compare your answer to those initial concentrations and see if it's that significant, right? See how different they are from each other. Yeah.
So if you know that, if we knew that we were gonna have to approximate, couldn't we just skip like the ice chart part to like save time?
Yeah, so we'll get to that. Essentially, skipping the ice chart and things like that, for these buffer solutions, you can use this Henderson-Hasselbalch equation that will present and avoid all of this. But yeah, so for this type of a problem, you wouldn't necessarily need to use kind of the ice chart if you didn't want to, right? I'm using it just to kind of go through, kind of the detail of everything and make sure we can all follow along. But yeah, in general, you wouldn't necessarily have to. Yep. Yeah, so I knew in the problem, I put in solution 0.1 molar KNO2, right? And I know that in solution, KNO2 is a strong electrolyte, which means it's going to form K plus NO2 minus, right? And so I know 0.1 molar of KNO2, right? Doing our sort of like stoichiometry, dimensional analysis, I forget what it's called in the Gen Chem, right? But based on my balanced chemical reaction, right, every 1 kind of mole or molar here of KNO2 is going, right here, I can say mole, right, will form 1 mole of NO2 minus, right? And so I know I get 0.1 molar NO2 minus, right? Because of that, right? So yeah, so it's just based off of the fact that this thing fully dissociates in solution because it's a strong electrolyte. No, again, all the salts we've been talking about in this class so far, and that we'll talk about that are relevant for exam 2 here, right, are all going to be strong electrolytes. Every salt, every ionic compound, right, is going to be a strong electrolyte, and so it will fully dissociate in solution. Okay? Near the end of chapter 17, we'll talk about salts that don't fully dissociate, that aren't strong electrolytes, but for now, everything that we're talking about are strong electrolytes. Okay. Other questions with this problem? All right. Okay, right, so, right, in kind of the acid-base chemistry that we're talking about in this course, right, in chapter 16 as well as in chapter 17, right, we have 2 types of acid-base chemistry going on, right? We have this equilibrium reactions established between weak acids and conjugate bases, and then we have our acid-base neutralization reactions that we've seen examples of and talked about and things like that, right, where I have some acid reacting with some base to form some salt plus water, okay? Okay. In this example, I have a strong acid with a strong base forming a salt, right, to a strong electrolyte plus water. So the net ionic equation for this reaction ends up being actually H plus OH minus going to H2O, okay? Because chlorine and sodium ions are just spectator ions in this reaction, okay? But in general, right, any acid-base reaction is an acid plus a base forming a salt plus water, okay? Now, there are a few examples where water doesn't get formed. For example, if your base is ammonia, NH3, then ammonia plus an acid will form a salt, right? But it won't form water because NH3 is a base that isn't donating, that doesn't have OH minus that it's giving off to act as a base, right? NH3 itself is accepting the proton. In bases like sodium hydroxide, right, the hydroxide is what's accepting the proton, right? The sodium is just this spectator ion, this passenger, if you will, in that acid-base reaction, okay? But ammonia here is the base in this bottom reaction. So it's accepting the proton, it forms H4 plus and Cl minus, right, which is a salt, okay, in solution, right? And again, this acid-base neutralization reaction occurs only between acids and bases that are not conjugate acid-base pairs. Again, I want to stress that multiple times, right? If you have an example like this example here, right, where I introduce nitric acid, okay, and potassium nitrite in solution, right? In solution, right? These are conjugate acid-base pairs. They do not react with each other. They just establish this equilibrium with each other, okay? Right, where the weak acid is on one side of the equilibrium and the conjugate base is on the other side of the equilibrium, right? They do not react with each other whatsoever, okay? But if I add, say, hydrochloric acid and sodium hydroxide, which are different acid and bases, right? They aren't conjugate acid-base pairs, then those will react with each other, right? Or if I add my HNO2 acid with sodium hydroxide, right? Those are different acids and bases, right? They aren't conjugate acid-base pairs. Those will react with each other, form a salt and water, right? But again, if you are a conjugate acid-base pair in solution, those do not undergo some sort of acid-base neutralization reaction. Okay, those establish just a weak acid, weak base equilibrium. Okay, right. So again, some more examples of this acid-base neutralization reaction, right? If I have CH3COOH plus NaOH, right? I have the paper here. I'll write these down, right? Write out what the products are for these reactions. For these two reactions, right, CH3COH plus NaOH is going to form what? So what here's the acid and what's the base on the reactant side? Right, this is our base. So this is our acid. Right, our acid donates a proton, so it's going to give up this guy, right? Okay. So it's going to donate that proton over here, right? And basically it's going to swap with the sodium here, right? So you're going to get sodium acetate, CH3COO, plus H2O, right? Salt plus water, right? And then this reaction, this is HCl, right? HCl plus CH3NH2, right? What is my acid and what is my base in that reaction? Yeah, acid is HCl, right? That is a strong acid. This is my base here, right? And so this is, right, my acid is going to donate a proton over here, right? Now this doesn't form water, but it does form a salt, right, of CH3 and H3Cl, right? Where CH3 and H3 plus is my cation and Cl minus, right, is my anion. Okay. All right. So again, right, these acid-base neutralization reactions, right, you're transferring some proton from your acid to your base, right, and that proton, right, is an H plus ion, right, so your acid is going to go down in charge, right, form some sort of anion. Your base is going to go up in charge, right, you're going to have some sort of cation getting produced from your base. That cation-anion pair, right, forms a salt, right, and so again, I formed the sodium acetate salt, right? And water is part of the products here. Here, I just formed the CH3NH3 cation with a Cl minus anion. Questions about these reactions here? All right. So everything we've been talking about is sort of alluding to a buffer solution. Okay. So anyone want to tell me what is, say, a buffer solution, how you might describe a buffer solution? Yep.
A strong acid with a weak base, or a strong base with a weak acid.
Yeah, so you can make a buffer solution by potentially combining weak acid with a strong base or a weak base with a strong acid, right? And what does that buffer solution do? Yeah, it sort of neutralizes pH. A buffer solution will make a buffer solution is a type of solution that is resistant to changes in pH with the addition of strong acids or strong bases into those solutions. Okay, right. So a buffer, right. Again, you can think of it as it's trying to kind of smooth things out, right? So it's trying to make it, right, a buffer solution is a solution where you add a strong acid and you don't get any large change in pH, See if I have, no, don't have that picture here. Right. But there's an example in the lecture video online, right, that shows that with the addition of like a couple milliliters of 1 molar sodium hydroxide to a neutral solution versus a buffer solution has a pH change of like 7 versus like 0.4. Okay, very different pH changes, right? Buffer solutions have very mild pH changes with the addition of strong acids or strong bases. Okay, right? This picture here on the bottom right, right, is here because your blood, right, in your body, right, is a buffer solution. So your body itself is a giant buffer solution and is resistant to pH changes. Okay, so the addition of some type of strong acid or strong base into your body will not drastically change the pH, which is very good because a drastic change in the pH of your body would cause very big problems for your health, basically. Yeah. Right. And so again, a buffer solution is a solution that resists changes in pH with the addition of strong acids or strong bases. Okay. Right. And we'll do an example of showing those resistances in just a minute. Okay. Right. So if I wanted to make a buffer solution, oh, right. I forgot to mention, right? So that's the definition of buffer solution, right? And we were told, right, how you can make a buffer solution by adding, say, a weak acid with a strong base or a strong base with a weak acid. And by doing that, what you do in the solution is you create a solution like this solution here of 0.1 molar acetic acid with, say, 0.1 molar sodium acetate, right? Where a buffer solution is a solution where you have roughly equal concentrations of an acid and its conjugate base. Okay, so right, so this very first example we talked about at the beginning of class today is an example of a buffer solution where I introduce into solution my weak acid and its conjugate base. Okay. Now another way you can make a buffer solution is by adding a weak acid in solution and some amount of a strong base to form the weak base. Okay. And we'll show some examples and talk about that, right? But another way to make a buffer solution is by adding the weak acid and the conjugate base just directly into the solution through the addition of some sort of salt, okay? Right? And so if I say have this acetic acid, right, as my weak acid in solution, right, I need to add its conjugate base, which is going to be what? Conjugate base of acetic acid. Yeah, the acetate in that sodium acetate is the conjugate base, right? And then I'd make a buffer solution by having a solution of acetic acid and adding to it something like sodium acetate, right, in order to make the buffer, right? So to make a buffer solution, often, a lot of times, you'll just add a weak acid with a salt that contains the conjugate base, okay? So often, okay, we'll use things like potassium, sodium salts, or nitrate or chloride salts, right, to add in the conjugate base or conjugate acid into our solution, right? So if I have acetic acid solutions, right, I add sodium acetate or potassium acetate to the solution to form a buffer. If I have, say, ammonia, a solution of NH3, right, ammonia, I would add ammonium chloride, right, or ammonium nitrate into solution, right, to introduce the weak acid, okay? And I do this because these nitrates, these chlorides, sodium, potassium, right, are very soluble ions, right? And so they are going to form strong electrolytes, and they're going to be spectator ions as well, right? The sodium, potassium, nitrite, chloride, right? These ions are spectator ions and aren't going to affect the pH or any of the chemistry involved in your solution, okay? And so we can kind of ignore them, essentially, when looking at the chemistry involved in any solution containing these ions, okay? Right, but again, so I can make a solution by adding similar amounts of my weak acid with my conjugate base. But again, the conjugate base, to add that, I need to add it in terms of adding a salt into the solution, right? Where I'm going to pick, highly soluble ions like sodium and potassium as a counter ions in those salts. So questions about the definition of buffer solutions, what makes a buffer solution, okay? How would you make a buffer solution? You needed to make one yourself. All right. So which of the following equimolar mixtures is a buffer solution, right? So this is saying, right, if I add, say, 1 molar of sodium hydroxide, 1 molar hydrofluoric acid, would that be a buffer? Or if I added 1 molar of H2SO4, 1 molar of HC2H3O2, would that form a buffer, right? Right. So when it's saying equimolar mixtures, right, you're adding, say, 1 molar of each thing to solution. In addition of 1 molar of each of these things, which one would make a buffer solution? Anyone have any thoughts of which of these 5 solutions would be a buffer? Got someone online saying E. Pull E's from online. Anything else? Any other thoughts? So let's look through these one at a time, right? So I have sodium hydroxide plus hydrofluoric acid, right? So let's say I have a solution, right, where I add sodium hydroxide and hydrofluoric acid in solution, right? Right, well, in this solution, right, sodium hydroxide is a base, hydrofluoric acid is an acid. These will react with each other because they're not conjugate acid-base pairs, and this will form sodium fluoride plus water, right? Now, if I add, say, 1 mole of this and 1 mole of that, they will both fully react, and I will get nothing left of this, and I will just have that left in solution. So a solution that contains equal molar of sodium hydroxide and hydrofluoric acid is going to be a solution that just contains sodium fluoride in solution, right? So that's just going to contain fluoride ions in solution that can potentially affect the pH. And so that's not going to be a buffer because I don't have the conjugate acid in solution, right? Because I've added equal molar of these two things, I will not have any of the conjugate acid left, right? HF here is your conjugate acid. I have none of that conjugate acid left in that solution. So this can't be a buffer because I just have the base, right? I need to have the conjugate acid and the base together. Okay? So A here will not be a buffer solution. Here, I'm adding a strong acid and a weak acid into solution. That's definitely not making a buffer, right? I need to add an acid and its conjugate base into solution, right, in some way. C here, I'm adding a strong acid, okay, and then a salt, right? Right, technically Cl is a conjugate base of HCl, but HCl is a strong acid, so it is not going to form any type of buffer solution, okay? Because you buffer solutions are solutions that have an equilibrium established between the weak acid and conjugate base, right? So you need to have weak acids and weak bases in solution, not strong acids and strong bases, right? So C will not form a buffer solution because this involves strong acids and its conjugate base, right? So that's not a buffer solution, okay? D here, I have H3PO4, which is an acid, and then I have sodium H2PO4, which H2PO4 is the conjugate base of H3PO4, okay? So D here will form a buffer solution, okay? This will form an equilibrium between H3PO4 and H2PO4, okay? And so this will form a buffer solution. While E here, the reason why it does not form a buffer solution is the same reason C does not. Because both E and C involve strong acids, right? And a strong acid is not forming any type of buffer solution, right? It's not forming any type of equilibrium, right? That's going to resist pH changes, right? It's just going to fully break apart in solution, okay? I need, right, this equilibrium that we talked about at the beginning of the lecture, right, to be established in a buffer solution for it to resist pH changes, okay? So in this example, okay, the only one of these things will establish any type of an equilibrium is with H3PO4 and H2PO4 minus. Yep.
What if sodium hydroxide and hydrochloric acid had different concentrations?
Then you would form a buffer solution. Yeah. So if I added, say, 1 molar HF and 0.5 molar NaOH, then I would form a buffer solution because I would have left some amount of hydrofluoric acid, and then I would have formed some amount of my fluoride. So yeah. So if the question A was not equal molar mixture but different amounts, then yeah, A could form a buffer solution as well. Mm-hmm. Yep. Other questions? All right. So for these buffer solutions, okay, so if you have a buffer solution, which is a solution that contains a weak acid and its conjugate base in solution, okay, so you have to have some non-zero concentration of a weak acid with its conjugate base. That's going to give you a buffer solution, right? If you have that, you use this Henderson-Hasselbalch equation to calculate the pH, okay, which is pH equals the pKa plus the log of the concentration of your base over the concentration of your acid, okay? Now the pKa, right, which was asked earlier, is just the negative log of your Ka, okay? So just like the pH is the negative log of the H plus concentration, right, the pKa is the negative log of your Ka, okay? So what we're going to do is let's apply this, talking about calculating the pH of some different buffer solutions. We're going to, I forgot to give the Ka for this example, so we'll actually just do this next example here. To do, that's kind of a three-part example, okay, to get the pH of a buffer solution, right, with the addition of, by itself, after we add some amount of a strong acid and after we add some amount of a strong base, okay? And we're doing part B and C here just to show how the pH does not significantly change with the addition of strong acids and strong bases. And we'll kind of talk about why as we're going through this example. Okay? So, all right. So for part A, right, what I have is I have a solution, right, by adding 0.14 molar HCNO into solution and 0.110 molar KCNO into solution, right? Now in the problem it says you add 0.14 moles and 0.11 mole, right? But then I'm putting it in a 1 liter solution, right? Which the concentration, right? The molarity is the moles divided by the volume. Since the volume is 1 liter, right? It's just the moles divided by 1. So that's why I just wrote down molarity, right? So if you're confused as to why I put molarity and not moles, it's because I just divided by the 1 liter of solution. Okay? And so the question is what is the pH of this solution, right? So again, if I see this problem, I say to myself, okay, I got HCNO, which is a weak acid. We're given the Ka, right, of HCNO is 3.5 times 10 to the minus 4. Okay. So the Ka is 3.5 times 10 to the minus 4 for this weak acid, right? And then I've added to the solution its conjugate base through the addition of a salt, right?
this salt KCNO will form K plus in solution plus CNO minus in solution, right? Where CNO minus, this is our conjugate base, right? So I have a solution that contains a weak acid and its conjugate base in solution. So that tells me I can use the Henderson-Hasselbalch equation in order to calculate the pH of the solution. So the pH is just going to be the pKa plus the log of the concentration of your base divided by concentration of your acid. Okay. Right, which this equation will be given on the exam. You need to know how and when to use it, but it will be given. Okay. Which again, when to use it is whenever you have a buffer solution. You have a buffer solution when you have a non-zero concentration of a weak acid with its conjugate base. Okay. And so all we got to do to get the pH is plug in here, right? pH is equal, right? The pKa is the negative log of the Ka, which is 3.5 times 10 to the minus 4. And then plus the log of the concentration of the base, right, which the base here is CNO minus, right? That's our conjugate base. It has a concentration of 0.11 molar. Concentration of our weak acid, HCNO, is 0.14 molar. Okay, so we plug all that in to get the final answer here. I didn't preemptively calculate these things, so I apologize for that. So just to do details, right, pH, this negative log of the pKa is going to be 3.46, and then the log of 0.11 divided by 0.14 is minus 0.10. Okay, so right, 3.46 minus 0.10 gives us a pH, right? So, right, that 3.46 minus 0.1, right, gives us a pH of 3.36. Okay. So that is the pH of our buffer solution. Okay. Right. So questions about part A here, about the use of this Henderson-Hasselbalch equation, why we were able to use it, how we used it. So part B, right, I have this same initial concentration, right, 0.14 molar, 0.11 molar of my weak acid, my conjugate base. And in this solution, I add 0.015 molar HNO3. Okay. What is the HNO3 going to do in a solution that contains HCNO and CNO minus? Right? I have added a strong acid that has a solution of a weak acid with its conjugate base. What is that strong acid going to do in that solution? If I add an acid and a base together, what will they do? Yeah, if they're conjugate acid-base pairs, they'll create an equilibrium. If they're not conjugate acid-base pairs, what will happen?
Create a salt and water.
Huh?
Wouldn't it create a salt?
Yeah, they will react together to make a salt plus water, right? So this HNO3, right? So I'm going to have this reaction of HNO3 plus my conjugate base of CNO minus, right? I'm going to have this acid and base will react together, okay? And this is going to form NO3 minus plus HCNO, okay? So, right, my acid and base react, okay? Right? Well, this reaction will go to completion, right? My strong acid is going to react until all of the strong acid is left. Okay, So if I start off initially with 0.015 molar of HNO3, my CNO minus, I start off initially at 0.110 molar of that. Okay. Right. Right, and then I start off with none of my nitrate ion, right, and then HCNO, I started off with 0.14 molar of this, right? So my initial concentrations of those three things, right, in this chemical reaction, right? So the chemical reaction that occurs is a reaction between the acid and the base in the solution, right? As long as the acid and bases are not conjugate acid-base pairs, they will react. And so these two things will react to form NO3 minus and HCNO, right? That chemical reaction is just kind of the transfer of the hydrogen from the acid to the base. Right, this reaction goes to completion, which means I'm going to use up my limiting reagent here of HCNO. So I'm going to lose all of my HCNO, right? Which that's going to react with equal amounts of CNO. And then that's going to form that amount of NO3 and 0.015 of HCNO. Sorry, I kind of lost some room for myself here, okay? And so after this reaction goes to completion, so here I'm making what I'll call an IC chart, ICF, okay, because this doesn't go to equilibrium, this goes to completion. So I know what the change is because I'm not establishing equilibrium. Everything's reacting on the reactant side that can, right? I have nothing of HNO3 left, right? For CNO, I have 0.1095. If I did that math correctly, no, I don't think I did that right. No, that's not right. Yeah, point, okay. Right. 0.11 minus 0.015, yeah, is not that, 0.095, thank you. That didn't seem right, 0.095, I apologize, so 0.095, okay. My NO3 is going to be 0.015. Doesn't really matter. NO3 is a spectator ion and all this, right? And the concentration of HCNO is going to then be 0.155, right? So 0.14 plus 0.015, 0.155. And so then, right now, after my acid has reacted with all of my acids react with the conjugate base, in solution, I just have left the conjugate base with the weak acid. And so this is going to establish, again, an equilibrium, right? And I can use the Henderson-Hasselbalch equation because, again, I'm just left with the conjugate base and conjugate acid pair, right, which is a buffer solution. So the pH of this solution is that pKa plus the log of the base divided by the acid, right? And then I know from before, right, that pKa is 3.46, so this pH equals 3.46 plus the log. Now the concentration of my base has decreased to 0.095. The concentration of my acid has increased to 0.155, right? So 0.095 divided by 155. And so this log comes out to be minus 0.21. And so my pH for the solution, right, is 3.46 minus 0.21, which is 3.25. Okay. Questions about what we did, why we did it, how we did it?
So for something like that, when you're adding acid, can you just kind of tell that it's going to lower the pH?
Yeah, I mean, you know for sure it's got to lower the pH because you are adding an acid, yeah, for sure, right? If you ever add an acid to a solution, the pH is definitely going down. If you ever add a base, the pH is definitely going up. So if it was some multiple choice question, right, and only one of the answers had the pH lowered from the original pH, then you know, without even doing any calculation, that's got to be the answer. Other questions about this problem? Yep. So yeah, so the pKa was 3.46 in both of these, right? And then this log of the base of the acid was different between part A and B, which gave us a final pH that's different between 3.36 and 3.25.
No, I think when you were writing the pH in part A, you just went from 3.36 to 3.4.
For part A?
At the bottom of part A, there's two different pHs.
Oh, well, so this is 3.46 minus 0.1. I apologize if right, that wasn't clear, right? But the pH is 3.46 minus 0.1, which ends up being, 3.36, right? So the pH here is 3.46 minus 0.21, which ends up being 3.25. Clear that up. Other questions? Right, and then part C is a similar type of thing, right, where now I've added, right, 0.015 molar of KOH, right? The KOH in this problem will react with my, right, I'm adding a base, so that will react with my acid, which is the HCNO, to form this will form K plus CNO minus. I'm going to write it like this, plus water. Okay. Right, this will form a salt and water. And I'm writing like this because really what we're concerned about is the concentration of CNO minus in solution, right? And then again, I can go through and do this initial change final, okay, to get the final concentration of my acid and the final concentration of my base, and plug that into my Henderson-Hasselbalch equation here to calculate the pH. Okay. Right. Right, which is just kind of filling out this chart, right? This would be 0.015. This is 0.14, 0.11 initially, right? Then minus 0.015, minus 0.015, and plus 0.015, right? 0.125, 0.125, okay? So you end up getting that as your final concentration of acid and base. So the pH is then equal to the pKa plus log of the concentration of the base divided by concentration of the acid, okay, which again, this pH is then equal to 3.46 plus the log of 0.125 divided by 0.125, which gives you a pH equal to 3.46. Because the log of 1 is 0, so that's how that ends up being there. Okay. But so that's how you do part C. I know I kind of brushed through it quickly, but part C is done the same way as part B. Okay. You just have a slightly different reaction because now you're reacting your base with your acid, okay, right? That strong base with your weak acid instead of reacting a strong acid with a weak base. Okay. So real quick, just to finish up kind of discussing about buffer solutions. So all of this is also worked out kind of in detail in the lecture slides and posted online as well. I forgot I had that worked out, so I didn't have to write all these numbers. But okay. But the final thing to talk about with buffers is buffer capacity. So often, so when we talk about buffer capacity for a buffer capacity, right? A buffer with a larger buffer capacity is a buffer that can absorb more strong acid or strong base, right? So the larger the buffer capacity, the more strong acid or strong base that buffer can absorb. right? Which basically means a buffer with a larger buffer capacity is one that has a higher concentration of your weak acid with conjugate base, right? So 1 molar HA versus 1 molar Na, right? And 1.1 molar HA with 0.1 molar Na, right? This first solution is going to be the buffer with the greater buffer capacity, just because it has more conjugate acid and conjugate base pair, right? Because again, if I have 1 molar HA, that means I can potentially react up to 1 molar of a strong acid, right? While if I only have 0.1 molar HA, then I can only react up to 0.1 molar of, strong base, right, of a strong base, okay? Right, so the more weak acid conjugate base that you have, right, the more acid or base, strong acid or strong base you can add to the solution before the pH changes drastically, okay? And so we call that having a greater buffer capacity. Say the buffer capacity is how much strong acid or strong base can that solution absorb before the pH starts changing by a lot. And again, that's determined by just the total concentration of your conjugate acid with conjugate base. Okay. And then the other kind of final point here, right, is this question is related. I forgot to kind of put on the slide, but before this, right? But basically, a buffer works best at a pH range equal to the pKa of that buffer. Okay, plus or minus 1 typically. So roughly, you take your pKa and add or minus 1, and that's kind of the pH range that this buffer works best in. Okay, so this question here is saying, which acid, right, weak acid would you mix with its conjugate base to form a buffer at around 1.5? Right, that question is basically asking, right, which of these weak acids has a pKa closest to 1.5, because that is going to be the weak acid that's going to be the best acid to use to form a buffer at pH of 1.5. Right, like if I'm in a lab and I want a buffer at a pH equals 4, I want to pick a weak acid that has a pKa closest to 4. Okay. And so, right, to solve this problem, you would take the negative log of each one of these Kas, right? And when you do that, I believe it's sulfurous acid here, B, has a pKa closest to a pH of 1.5. Okay? And after the exam, we'll see more about these buffer solutions and how the relationship between pKa and pH and their buffer range and things like that. Okay, but the ideal weak acid conjugate base pair for a buffer solution is that has a pKa close to the pH you want, within a value of plus or minus 1 pH units. Okay, and again, buffer capacity is referring to how much strong acid or strong base can your buffer absorb, and that just directly depends on how much weak acid and conjugate base do you have in solution. So questions about what is a buffer solution, how we can calculate the pHs of buffer solutions, buffer capacity, what makes a buffer solution again, anything we kind of talked about today. So again, right, as a reminder, starting Monday, we'll have an exam 2, okay, for Monday, Wednesday, right, which will include this topic of buffers, okay, on the exam, as well as chapters 15 and 16 and 20. Okay. Again, there's a review thing posted on Canvas. Yeah, you will be given the Henderson-Hasselbalch equation. So for example, the list of equations in this kind of study guide, right, has the Henderson-Hasselbalch equation here, right? But again, I note that this will be given to you. Okay. So I note, just like for chapter 20, if you need to use an integrated rate law, that will be given. So I note which equations will be given and which equations won't be given. on this kind of study guide. Okay. All right, which again, it adds 3 pages to it. First page discusses topics, concepts, and types of problems that you should be comfortable with. Second page is equations. Last page is resources and things that you should review. Okay. Any questions from those here on Zoom before I close out the session? All right. Doesn't seem like it, so I will close out the Zoom session and see those who are taking the exam on Monday.